Hello guys, in this lesson we will study the roots of a function. A root is a value of x for which the function equals to 0. Now finding the roots help us understand where the graph intersects the x-axis. First, let's remind ourselves what a root actually is. So a root is an x value where the function equals to 0. Graphically, what does this mean? It means that the point where the graph crosses or touches the x-axis. So when we talk about finding the roots, we are really looking for where f of x is equal to 0. Now, graphically, the function may intersect the x-axis at more than one root, as you can see in graph 1, or in one root, as you can see in graph 2, or it may have no roots, as it is clear in graph 3. The graph does not intersect the x-axis at any point. So we have said that the function may cross the x-axis at more than one point, or it may have no roots at all. So how can we find or figure out the number of roots of a function? To do that, we need a very important idea, which is whether the function is monotonic or not. What do we mean by monotonic function? Monotonic means it is either always increasing or always decreasing. In the graph above, you can see that the function increases, decreases, then increases again. So the curve changes direction several times. We are talking here about interval minus 4, 4. So because of these changes, the function crosses the axis more than once, which means it can have several roots inside the interval. So if the function is not monotonic, it may intersect the x-axis at more than one time. What do we mean by not monotonic? Not monotonic means it's not increasing, neither increasing always nor always decreasing. It changes direction more than one time. Now look at the above graph here. This function is monotonic because, as you can see, it is always increasing. It moves in one direction in the interval shown. So when the function is monotonic, always increasing or always decreasing, in this case the function is always increasing, it will cross the x-axis only once. This means that the function will have a unique root. Let's solve these two examples, which will illustrate the idea more clearly. So in example 1, you have f of x equals x cubed minus 2. F prime of x is equal to 3x power 2. 3x power 2 is positive, which means that f is always increasing. If you solve f of x equal to 0, means x cubed minus 2 equals to 0, x cubed equals 2, x is equal to the cubic root of 2, you will note that the function has a unique root. Now, since the function is always increasing, means monotonic, it has one unique root. Meanwhile, in example 2, f of x is x squared minus 4. If you find f prime of x, it is 2x. On R, 2x is greater than 0 when x is less than, 2x is less than 0 when x is between minus infinity and 0, and 2x is greater than 0 when x is between 0 and plus infinity. So this function is not monotonic. So if you solve x squared minus 4, or f of x equals 0, so x squared minus 4 is 0, x minus 2, x plus 2, this is the factorization of x squared minus 4, is 0, so x is 2 or x is negative 2, the function admits 2 roots. So since the function is not monotonic, it admits more than one root. Example 3, f of x equals x cubed minus 3x. As usual, we will find f prime of x to check whether the function is monotonic or no. Now f prime of x is equal to 3x power 2 minus 3. Now if you solve f prime of x equal to 0, you will see that it will be equal to 3 into x squared minus 1 equal to 0. So 3x minus 1, x plus 1 is 0, x equals 1 or x equals to negative 1, which means that f of x has local maximum and local minimum. Local maximum 1, local minimum negative 1. So sure, f is not monotonic. If you solve f of x equals to 0, you will have x cubed minus 3x is 0, x common factor, x squared minus 3 is 0, x into x minus radical 3, x plus radical 3 is 0. So x is 0, x is radical 3, x is negative radical 3. So the idea here is that a non-monotonic function can have more than 2 roots. Now this theorem tells us whether a function admits a root over an interval or no. So if f is a continuous function over an interval ab, so that f of a times f of b less than 0. And what does this mean? This means that one of the values is negative and the second is positive. Either f of a is negative and f of b is positive, or f of b is negative and f of a is positive, for the product to be negative. Then the equation f of x is 0 admits at least one root alpha, where alpha is between a and b. Why does this happen? Because if one of the roots is negative and the other is positive, this means that the function will pass from negative to positive. So sure, it will pass through 0. So if f of a times f of b is negative, then there is a root alpha between a and b. Now if the function is strictly monotonic, then this root will be unique. Now given these two examples, what you have to do here is to check whether the functions have roots inside the given intervals, yes or no. So we will start by example 4. F of x is x cubed plus x plus 1, a polynomial, so sure f of x is continuous. This is the first condition of the theorem satisfied. So f of x is continuous. Now let's find the values of f at the endpoints, so of the interval. f of negative 1 is minus 1 minus 1 minus 2 plus 1, so minus 1. F of 0 is equal to 1, so f of minus 1 times f of 0 is less than 0, which means that the function admits at least one root alpha, a root alpha between negative 1 and 0. Now, to check whether it admits one or more roots, you check the monotonicity of the function. How? By finding f prime of x. Now, f prime of x here is 3x squared plus 1, greater than 0 always. So, the function is increasing. The function is increasing. So, monotone. So, monotone. So, the root is unique. Now, in example 5, same thing. The function is continuous since it is a polynomial. So, f of x is continuous. We find the values at the endpoints. F of negative 2 is negative 8 minus 3 times minus 2 plus 1. So it is minus 8 plus 6 plus 1 minus 8 plus 7 minus 8 plus 6 plus 1 minus 8 plus 7. So it's negative 1. F of 2 is 8 minus 3 times 2 plus 1. So it is 8 minus 6, 2 plus 1, it is 3. Also, f of negative 2 times f of 2 is less than 0. So the second condition of the theorem is satisfied, which means that the function admits at least one root alpha between negative 2 and 2. Now, to check whether the root is unique or no, also you check the monotonicity of the function by finding f prime of x. Now, f prime of x here is 3x squared minus 3. The function has a local maximum and a local minimum. So f of x is not monotone, which gives us that we may have more than one root.